In this work, we present adapting skills to novel grasps, a self-supervised approach. First, consider a skill which is defined as a sequence of end-effector poses or velocities that define the trajectory of the end effector. For example, here, we see the trajectory followed by a hammer to hammer a nail. Then, consider such a skill that was tailored to a specific grasp pose of an object in the robot's gripper, like the grasp of the hammer or the grasp of the glass shown on the video on the left. Our method is designed to adapt the trajectory of each skill to possible different, novel grasp of the object as shown in the middle pair of videos. This is important since deploying these skills naively without adaptation leads to task failure as shown on the videos on the right. To achieve this, our method collects data fully autonomously in a self-supervised manner without any human effort, while requiring no prior object knowledge, such as a 3D CAD model. Our method can work only with RGB images if required, or also depth images as well if needed. Our method is robust to noisy and partially missing depth data if using depth images, and also it does not require any camera calibration. Specifically, consider a skill such as using a hammer to hammer a nail that is taught to the robot using a human demonstration that is tailored to a specific grasp pose of the hammer. We refer to that specific grasp pose as a skill grasp, and an example of the human teaching the robot with a skill grasp how to hammer a nail using kinesthetic teaching is shown on the first video on the left of this frame. If during skill deployment the robot grasps the hammer differently, for example by using an off-the-shelf grasping method, then naively deploying that skill for the novel deployment grasp leads to task failure, as shown in the second video. As such, our goal of our method is to find a corrective transformation, denoted CTEE prime, to move the end effector such that the hammer under the novel deployment grasp moves to the same pose as the skill grasp. Then, we can transform the skill's trajectory by the corrective transformation to adapt the skill such that the hammer grasped under the deployment grasp follows the same trajectory it did under the skill grasp. The video on the left here shows the trajectory followed by the hammer under the novel deployment grasp after transforming the trajectory with a corrective transformation. As shown, it matches the trajectory demonstrated by the human when the hammer was grasped at the skill grasp, as shown on the video to the right. So, how does our method learn that corrective transformation to adapt skills to novel grasps in a self-supervised manner without any prior knowledge? The robot grasps the object first at a random pose. We refer to that pose as the reference grasp. The reference grasp can be any arbitrary pose. It can be a random pose. The robot may grasp the object automatically using an off-the-shelf grasping method, or a human might just simply place that object in the gripper in a natural-looking pose for that object. Then, the robot moves to some random pose in front of an external camera. We refer to that pose as the reference pose of the robot, and that pose can be any pose as long as a grasped object is visible to the camera. Then, the robot begins to move to random poses in front of the external camera while the object is rigidly grasped in the end effector. No human is involved in that process. During that time, the robot records images and the corresponding end effector poses using forward kinematics in a self-supervised manner. So why is this process useful? When moving the end effector from the reference pose to some random pose, denoted NTEE prime relative to the reference pose, the image captured from the external camera depicts how the object, for example the hammer, would appear to the camera if it was grasped at that pose relative to the camera when the end effector is also at the reference pose. As shown in this example, here on the left, the move relative to the reference pose emulates the arbitrary grasp shown in the middle. When collecting self-supervised data, we record an image of the robot and the object as well as the corresponding transformation NTEE prime. An example of the collected dataset is shown on the left. Consequently, each data sample comprises a tuple of the image captured from the external camera and its corresponding NTEE prime. When the robot is at the reference pose and the object is grasped as shown in the arbitrary grasp, transforming the gripper by the inverse transformation of the corresponding transformation NTEE prime, while the object is rigidly grasped in the gripper, moves the object to the same global pose as the reference grasp. In practice, we leverage that data, segment each image, and train an alignment network that takes in the segmented objects and predicts the inverse transformation NTEE prime. Then, to adapt a skill to a novel grasp, first, we move the robot to the reference pose and capture an image of the skill grasp used to define the skill's trajectory. We use the alignment network to obtain the transformation that aligns the skill grasp to the reference grasp. Here, instead of denoting this transformation as NTEE prime inverse, as denoted before, for clarity, we denote it as STEE prime. Then, for a novel deployment grasp, we also perform the same process and obtain the transformation that aligns the deployment grasp to the reference grasp. We denote it here as DEE prime for clarity. Finally, by multiplying these two, we obtain the corrective transformation which we leverage to adapt the trajectory of a skill to a novel deployment grasp. Here is an example deploying the full pipeline after training the alignment network for a particular object. Consider the skill grasp of the hammer depicted on the left. The robot, in front of the external camera at the reference pose, uses the alignment network to predict the transformation that aligns the hammer to the reference grasp. A human then provides a demonstration on how to hammer the nail with the skill grasp. Then, when the robot grasps the hammer at the novel deployment grasp, we use the alignment network to obtain the transformation that aligns the deployment grasp to the reference grasp. Note that simply deploying the skill naively without any adaptation leads to task failure. As shown below here, the hammer fails to hammer the nail successfully. However, after using the two transformations that we obtained using the alignment network and computing the corrective transformation, we can adapt the demonstrated trajectory such that the skill succeeds. Here is another example for a different deployment grasp. Here is an overview of the skills taught with imitation learning adapted to different novel grasps. And finally, here's an example of our method adapting skill trajectories for highly precise peg and hole insertion. Thank you a lot for watching, and for more information regarding the method and more experimental results, please read our paper and visit our website. Thank you.